understand the way that cells function in batteries, you have to remember the stuff that we did, I don't know, way back in chapter 3 with redox reactions. And so first of all, you have to remember definitions of oxidation and reduction and how to look at an overall equation and determine what thing is being oxidized and what thing is being reduced, because that's going to be like the basics behind how everything else works. So real quickly, the acronym or whatever it is to remember oxidation and reduction, what is it?
Leo.
Okay, which tells me that oxidation is losing electrons, reduction is gaining electrons. Okay, so I mean, remembering that is not hard, and remembering those definitions is not hard, but you have to be able to apply that. So now looking at this equation, you have to be able to figure out which one has lost electrons and is therefore oxidized, and which one has gained electrons and is reduced. So in order to do that, you have to assign oxidation numbers. Oxidation numbers are kind of like charges, not exactly. I mean, it's kind of just a way of keeping track of electrons. So looking at this equation, if I were to go through and assign oxidation numbers to everything here, solid iron, anything that is in its elemental state would have an oxidation number of what? 0, okay? So this one is 0. In here, hydrogen and chloride ions, hydrogen ions are, well, +1. Chloride? -1. Okay, and then over here, if my chloride ions are -1, then that makes this iron what oxidation number? +2. And H2, elemental state, oxidation number is 0. So in order to figure out which one's being oxidized and which one is being reduced, you look at how those oxidation numbers have changed. Chloride ions stayed -1 the whole time. Iron went from 0 to +2. So was that a gaining or losing of electrons? Losing. So that is oxidized. And then the other one, hydrogen. Hydrogen went from +1 to 0. That was gaining electrons, so hydrogen is the thing being reduced. Now, you have to be able to take this equation and pay attention to the half reactions. The half reactions is just looking at the thing that's being oxidized in one equation and the thing that's being reduced in another equation. Now, when we were balancing redox reactions and all that stuff, that's not really part of chapter 17, but you know, you kept all these things in there even if the oxidation number stayed the same. But when we're dealing with electrochemical cells, fancy way of saying batteries, you only deal with the things that change in oxidation number. So here, the half reactions for this, I would have iron going to iron 2+. And then what else is part of the half reaction? I need +2 electrons. Okay, so the electrons, although they're not shown in this overall reaction, the half reactions show where the electrons are. Okay, for the oxidation, the electrons are on the product side. For the reduction, I've got 2 hydrogen ions. The electrons are on the reactant side because it's gaining electrons to be reduced. So that's my reduction half reaction. This is my oxidation half reaction. All right. The rest of chapter 17 is all kind of based on these half reactions and how they work together to allow the flow of electrons to create electricity. So before we talk about how this all comes together to form a battery, we need to talk about how each half reaction has something called a reduction potential that is assigned to it, what it means, and how we're going to use that to calculate the overall voltage of a battery.
That literally hates me. Every time I've used that sharpener, the tip is just falling off.
I don't have any problems.
Skills here, aren't you?
No, I just put it in just like that.
Yeah, we need to steal from.
Oh, hey, maybe this one will work better.
Oh, it's a Stanley Boston. It is a Stanley Boston. I'll try.
Stanley Booth.
Volunteer.
You can still steal Brahmas,
I didn't know I had this, or I would have busted it out
Stanley
sooner.
Booth. Yes, the one
We're doing
Stanley
Dr.
Boston staples and paint up.
I
Smells
know.
nice.
It's
It smells like it's that new pencil sharpener smell.
Oh, yes.
Yeah, it's very familiar.
Yeah.
Is it plugged in? Okay. Oh, you pushed too hard, that's why.
Yeah.
Broke it.
Oh my god.
Ready? Okay, let's see.
Yeah. She's gonna use some GarageBand to edit this.
I mean, Sam is waiting to like write a poem about this.
So that's what Stanley Boston was a staple. It is.
It says Boston. It is a Stanley Boston. Is it amazing?
Okay, here we go. Every half reaction.
That is a high quality pencil sharpener we got right there.
Back to this. Okay, every half reaction. There's a whole big
Postage pencil.
list of half reactions on page 796 of your textbook. It has pretty much all of the common half reactions and the voltage values that are assigned to it. So every half reaction has some kind of voltage or reduction potential that is assigned to it. That word electric potential, if you see that, it pretty much just means voltage. You'll talk a lot more about electric potential and stuff in physics. Now you just have to know it means volts, okay? And you've heard of voltage before. So they are always given as reduction potentials, meaning that if I were to look at, and I'll put this back up in a minute, this is the table on page 796 with a bunch of different half reactions. If I look for the one that we just kind of talked about, that is iron and iron 2+, all of these reactions are given as reduction reactions. And so you have to pay attention to that. If it's actually the thing that's being reduced in the overall reaction, then you leave this number the way it is. But if it's the thing that's being oxidized, then you have to take this reduction potential and you have to change the sign. You have to make it the opposite. So instead of it being negative, you would make it positive 0.44. And you use that to figure out the overall cell potential. So they're always given as reduction numbers. If it's oxidation instead, then you flip the sign. Also, the larger the potential is for the half reaction, the more likely it is to occur, which is just a fancy way of saying the larger value for E, that little curvy E is just how you represent electric potential. The larger electric potential is going to be the one that's reduced. Like if you have two that you're comparing, if they don't give you the overall reaction, but they say, here's the two half reactions. The one with the larger E is the one that's being reduced. The one with the smaller electric potential is the one that's oxidized, which then you have to flip and change the sign for.
Wait, reduction potential and electric potential synonymous?
Yeah, they're the same. The reduction potential is the electric potential for the reduction reaction.
I understand completely.
Okay? The reduction potential is the electric potential for the reduction reaction. And then if it's the one that's being oxidized instead, you just have to flip it. Okay, so then, and we're going to do all of this when we look at a specific electrochemical cell. But this then would be the equation for calculating the total voltage or the total electric potential of the battery. And then we'll go ahead and write down this general stuff about a galvanic cell, and then we're going to do the whole drawing the diagram and seeing how the electrons travel through the cell. Okay, so a battery is just a bunch of galvanic cells put together. So it allows the electrons all to flow, and it has a certain amount of chemical potential energy that's stored within the battery. So I mean, the whole thing that's allowing the battery to run is a chemical reaction that's going on. And we're going to diagram all the different parts of that reaction here in just a minute. But once that chemical reaction runs out of stuff, then the battery is dead. It doesn't work anymore. And that chemical potential energy is turning into electrical energy. Electricity is just moving electrons, which is why all these redox reactions are kind of the whole basis for batteries, because you have electrons being transferred. All right, let's go ahead and look at an example. All that matters when we're talking about these electrochemical cells is the actual stuff that's being oxidized or reduced. There are other ions involved, there's other stuff that's there, but it's not involved in the actual transfer of electrons. So when you're dealing with overall reactions for a galvanic cell or any kind of electrochemical cell, you always have pretty much two things. One is going to start off as a solid and change to an ion. The other one starts as an ion and turns into a solid. And so from this overall reaction, you can see that zinc is being oxidized, losing electrons. Copper is gaining electrons and is being reduced. You have to be able to, most of the time they give you kind of the general diagram and you have to fill in stuff with it. So the general diagram is basically you've got two kinds of reactions going on, or you've got two things. You've got one part of this is being oxidized and one part of this is being reduced. And so if we were to separate this into two half reactions, the half reactions are kind of split up into two parts of the cell, where you have one side being the oxidation side and one side being the reduction side. Now, I'm dealing with, in this reaction, I've got zinc and I've got copper that I'm dealing with. So on one side, I'm going to have an electrode, which is just a piece of solid metal that is made up of one of these things that conducts electricity, okay? So I've got one electrode that's made of zinc, and I've got another electrode over here that's made of the other metal, which is copper. Those electrodes are placed in solutions that have these ions floating around in there, okay? So this is going to be a solution of something that's going to have zinc, some salt that would ionize, so maybe it's zinc nitrate. So if I put zinc nitrate in water, it'll break apart into zinc ions and nitrate ions. Okay, so there's a solution on that side. Over on the other side, the solution that fills up that side would be one that has that ion of the metal. So I would maybe have copper chloride. So copper ions, chloride ions. So in this particular reaction, the nitrates, the chlorides, they don't really matter. It's all about what's happening with the metal ions and the solid metal electrodes. Okay, those electrodes are connected by some wire. Now, in the actual like cell or battery itself, it would just be a whole wire connected through. But on the diagrams, they normally show it connecting to like a voltmeter. So it'll say like what is the reading on the voltmeter. So you measure like the voltage of the whole cell. Okay, so it's connected. Now, what else? In this particular overall reaction, they've given us what's happening. Zinc is going from solid zinc to zinc 2+. So I'm going to label over on this side the actual reaction that's happening. So zinc to zinc 2+, it's losing electrons, so it's being oxidized. So this is the oxidation side. And even if they don't ask you to label that, it's helpful to do because it'll ask you other things later on that require you to refer back to which side is being oxidized and which side is being reduced. So if you have it labeled ahead of time, it makes it easier. Over here, I've got copper gaining 2 electrons and being reduced to solid copper. So this is my reduction side of the reaction. Now, in addition to all of this setup with the solutions and the electrodes and the wire connecting the electrodes, every galvanic cell, so this is one cell, lots of cells put together make the battery. Every galvanic cell has something that is called a salt bridge that is necessary for the cell to function. Now, being that the name of this is the salt bridge, what do you think is inside of it?
Salt.
A salt. A salt solution. And it can be, remember, a salt is any kind of ionic compound. So you're going to have a solution in there that has some ionic compound dissolved in it so that it ionizes. So maybe I have a solution of sodium nitrate, okay, which will then ionize into sodium ions and nitrate ions. Now, we're going to talk about, I'm going to first let you guys write down definitions for anode, cathode, and then some stuff about the salt bridge. We're going to talk about why that salt bridge is important and why the cell can't function without it. And then what happens to the ions that are inside of it is also important. So go ahead and write this stuff down, and then we're going to label some other stuff up here on this diagram. You have probably heard of the terms anode and cathode. But you have to be able to now label the different parts of this diagram as one of those two things. And so you need to also, in order to be able to label them on the diagram, have the definitions memorized. So the anode is where oxidation occurs. The cathode is where reduction occurs. Easy way to, I don't know why electrochemistry has all these like funny ways to remember stuff, like Leo and all that stuff. If you can remember an ox and red cat, then you can remember these definitions. Okay? The anode is where oxidation happens. The cathode is where reduction happens. So oxidation, that's my zinc side. So that is the anode. Mitchell. The reduction side is the copper side. So this side over here is the cathode. Okay, so it'll ask you to label those things. Also, it'll ask you to label the flow of electrons. Like, do the electrons go from left to right or do they go from right to left? Now, you should be able to see based on your half reactions that electrons are leaving this side and going towards the copper side. But if they don't give you those half reactions, if you don't have that information, the electrons always flow from the anode to the cathode. And okay, the purpose of the salt bridge. The purpose of the salt bridge is to keep the charge in each one of these compartments neutral. Okay? So that wouldn't happen without the salt bridge because I'm adding electrons to this right side over here. So I'm gaining more and more negative charges. And then this one, this side over here is losing electrons. And so since I'm gaining electrons over here to this right side, the sodium nitrate, one of those ions is going to come in here and be added to this solution to balance out the charge. So since I'm gaining negative charges over here from the salt bridge, I have to have positive ions enter into that solution to kind of balance out that charge and make the whole thing neutral. On the other side, on the left, it's losing electrons, which is making this side become more positive. And so if it's becoming more positive, then the negative ions from the salt bridge will enter into that solution to balance out the charge. So that's a really, really common question, is to say, what's the flow of ions from the salt bridge, and to be able to explain why. All right, so then the next part of the question, I think we've done everything up here. The next part of the question is to figure out the total voltage of the cell. These are the half reactions that will be given. Okay, so in the problem, they will give you the reduction potentials for each half reaction. And remember, they're always given as reduction potentials. So, you guys put those away. They give them to you as reduction potentials. And so what you need to pay attention to is which side is actually being reduced and which side is being oxidized. The copper side is the one that's being reduced. If it's the side that's being reduced, then this number stays exactly the same the way it is. So it stays positive 0.34. The zinc is the side that's being oxidized up here in our diagram. So Since it's given to me as a reduction potential, but the zinc is actually being oxidized, what do I have to do to this number? I have to flip it. I have to make it, it's not going to be negative, it's going to be positive 0.76. When you add you basically add the numbers together, but it's the electric potential for the oxidation plus the electric potential for the reduction. When you add those two numbers together, you get 1.0 or 1.10 volts. That is the voltage of that particular cell. And positive voltage numbers represent spontaneous reactions, so they'll start to ask you about that as well. Or thermodynamically favorable. If it produces a positive voltage, it means the reaction's kind of happening on its own. All right, just go ahead.
System would require energy to make this.
So if you got a negative voltage, those would be like, and we're going to talk about this on Friday, but like rechargeable batteries, when you have to plug them in, and then basically it makes the reaction happen in reverse, so that it like recharges up the battery, so that you have all this stuff over here again, so that the electrons can flow back. That's why. All right, other wording that you need to be aware of. Sometimes they won't just give you the overall reaction, but they'll start to tell you about what kinds of things will form as a solid, and that's going to be a hint to you as to what's being reduced and what's being oxidized. So you have to be familiar with those terms. If they tell you in the wording of the problem that something solid is forming, in this particular example that we talked about, they would say solid copper is forming on the zinc electrode. Well, just the wording of you knowing that solid copper is forming, that means it's going from the copper ion to the solid copper, which means that it's being reduced. So anytime it tells you about that solid forming, you can use that as like a hint to tell you that the copper is the thing being reduced, and therefore then the other thing, the zinc, is the one that's being oxidized. Okay, do we have all that? I just have one more thing. And I'm serious, it's only one more thing. We're going to make this D, because we don't need that other thing up there yet. And that is, okay, all of those electric potentials, looking back at this, when you have these solutions in this different half cell reactions, all of these solutions and their electric potentials are measured at concentrations of 1 molar. So assuming that all the concentrations in here are 1. Now, if those concentrations change, like they say, okay, we increase the concentration over on this side, what does that happen, or what does that do to the overall voltage of the cell? Which is really kind of a Le Chatelier question. So I'll let you write that down, and then we're going to apply it to the equation that we just did. And then that's it.
cell potential, like electric potential for the entire.
The whole thing, yeah. Okay, so this was our overall reaction that we had. And then if the question is, if the zinc concentration is increased, which basically just means, okay, I take more zinc nitrate, and now this concentration is not 1 molar, but it's something higher than 1 molar. What does that do to the overall cell potential, or the overall voltage of the battery? Now, if I add zinc, it's like a Le Chatelier's question, because what you want to do is you want to pay attention to where that zinc ion is in the equation. So if I increase my concentration of zinc ions, zinc is over on the product side of the reaction. So putting that there, putting more of that there, kind of stops the forward reaction from happening. The forward reaction produces positive voltage. So if I put something over here that stops the forward reaction from happening, it's almost like shifting, it would shift it to the left. And so the voltage would decrease. Since the forward, oh, we should maybe write that. The forward reaction produces voltage. So yeah, if I stop that from happening as much, then it's not going to produce as many volts of electricity. And then if I were to increase the concentration of copper, something on the reactant side, then it would make the forward reaction happen more, and you would have increased voltage on your cell.